Hello everyone and welcome back to part 3 of the Q Learning tutorial series. Super excited to get into this. This time we are going to be working on sort of the observation pre-processing and also a little bit on the experience replay, which, I will explain what that is. If you haven't watched parts 1 or 2, definitely watch those. This is, again, part 3. So last time, quick review, we got our environment working, we made a little loop to take actions, and then we also made the architecture for our model. So what are we going to do this time? This time we are going to, well, I just said that, the observation sort of pre-processing and the experience replay. So let's get into that. So before we start out, let's get an example observation that we can work with, right? So I guess we can just sort of do in, what is it? I should probably need to run this first. Once we have that run, we can just do a quick env.reset, right? It'll reset the environment and get us an observation. Now this observation should be of the shape, there we go, 210 by 160 by 3. So what do we want to do with this? So what do pixels look like, I guess, first is the most important question we need to understand. And it's fairly simple, right? You have this 2D array, and after that, you have 3 channels that represent the R, G, and B values, how much red, how much blue, and how much and green and red, green, and blue. And what we want to do is right now, those are between 0 and 255 inclusive, right? But when we're feeding data into a neural network, we generally want that to be in the space of like 0 to 1 or something, right? We want to normalize it, or not normalize it, but just change the range to be 0 to 1. Otherwise, they tend to not work very well. So that's the first thing we want to do. So we want to, I guess we can write this out, right? We want to change the range to 0 to 1 of all the pixel values. For example, right now, if we do probably like obs, we can do like max of obs dot reshape -1. If we do this, right, so the maximum value there right now is 200 out of 255, and then the minimum we already should know is 0. And that's just what's there. It's not the maximum possible value, right? So that's the first thing we want to do. The next thing we want to do is we will actually need to have some, imagine we're playing the game, right? And you see the first frame of the ball, right? So we have some ball, we have some bricks on top, and then we have our paddle on bottom. One issue is if you're looking at this frame by frame, we don't have any concept of the past, right? We only have the concept of the current frame, what's happening right now. And that can prove to be sort of an issue because that means we don't necessarily know if the ball is moving up or down, right? If we don't have any concept of what was happening before this current state. And because of that, we want to stack essentially multiple frames on top of each other so that the agent can essentially see the change over time. And from that, it should be able to infer whether or not the ball is moving up or down, or sort of the order things are happening in. So that's the second thing we want to do, stack frames. We will specifically be stacking 4 frames at a time, as that's just what's most commonly used in papers. Let's see, other than that, thinking, and I think we should be good. So let's actually get to writing those functions. So the first one is right here. So I'm just gonna, and we need to resize it, that's right. Resize, we will be resizing it to, I believe, right now it's 210 by 160, so we'll be resizing it to 110 by 84, or vice versa. But that's another thing, just simply to make the process go faster. I mentioned, I think in the last video, that they use an 84 by 84 in the original DQN paper. However, they did that because of a limitation with the actual libraries at the time. They had to be in a square shape. We don't have that limitation, so we're just going to be using this. I believe, and then, sorry, there's one last thing, is we're going to be converting it to grayscale. Honestly, I have a feeling this would probably work without doing this. We're just doing it for the purpose of making everything as simple as possible, and I believe that is the way they did it in the original paper. So just to stay true to that and get sort of as close in implementation as we can. So the first function I have for us is this filter obs function, right? So this just checks to make sure the sort of the observation we pass in is the right sort of the right, because we're only processing one at a time, so we want to make sure it's a three-dimensional thing, the width by the height by the number of channels, and then we also want to make sure it's a NumPy array. The next thing we want to do, and this is where our CV2 comes in if you don't have that import yet, we want to resize it. The resize shape in our case is going to be 84 by 110, and this is actually backwards, I believe, so this will actually come out as 110 by 84. I might be wrong there. We'll double check in 1 second. And then the interpolation is interlinear. This is just the way it basically shrinks it. I believe there's other options, and other options might work just fine. I know this one works fine though, so we'll be using this. So then the next is to convert the color. So we're converting the color of our observation to from basically color to a grayscale. And then after that, we're converting the observation to the scale of 0 to 1, because before the highest value was 255, so now it should be 1, and the lowest should of course still be 0. So let's run this and make sure it works, right? So we have our test observation here. So let's pass it into filter obs and see what we get. Okay, so let's check the shape. It is, so it's 110 by 84, so that's good. So this is, again, this is reversed, which is a little bit weird, but I believe it's because of the fact that in general, right, you have the rows first and then the columns second, but you have the width first and the height second when you write it out generally. But like the number of rows corresponds to the number to the height, not like vice versa. Anyway, small side tangent there. But anyway, so we have the right shape. Let's, I guess, make sure that we have, as you can see, we also only have one channel because we converted it to grayscale. And then the last thing I want to check is just make sure, we'll check what the range of values here is, so we can do like a max over shape 1. So the max should be no greater than 1. Yeah, so it's 0.55. Cool. And then what is the min? Should be 0. Awesome. So it looks to be working. I can tell you it is working. I've done some more testing. So we have our observation filtered. That's cool. We can probably actually show it if we want, like a plt.imshow. I don't know if this will actually work, but it should theoretically have no problems of the observation. There we go. Cool. So it's grayscale, so the colors are a little weird, but you can see that everything looks perfectly fine. We've scaled it down, but everything's still there. You might notice the ball is not there. That's because this is the first state, like this is the first step of the reset environment. The game hasn't actually started yet, so that's perfectly fine. But all the bricks are there. The paddle's there. Looks pretty good. So now that we know that's working, the next thing we want to do is start stacking observations. So we want to essentially make a function that can stack one observation. And the way that will look is we will essentially have then a shape of, if we're stacking 4 observations, it will be something like the shape for, what was it, 110? Yeah, 110, 84. And that would be a single pre-processed observation. So let's do that. So this one's going to be a little bit weird because we're actually going to have 2 inputs to our function. We're going to call it get stacked obs. We're going to have, so of course, our current observation, and then also the previous frames. So we do need some way of knowing when to, like, an episode resets, because we don't want to reset an episode and then keep using frames from the last episode, because that'd be a little weird, right? When we restart, what we're going to do is we're just going to copy the first frame 4 times. So I guess there's probably other ways to do it too. You could maybe use zeros, but that's just what we're going to do. So first we want to say if not pre-frames. And previous frames, this will just be an array or a list we pass in of the previous frames. So if there's nothing there, we want to fill it up. So we'll say previous frames equals the current observation times, and let's make a sort of a constant up here called in frames, and this will be the number of frames we're going to stack. We'll say it's 4 for now. And we're going to multiply that by in frames minus 1. So we'll get 3 frames here. And then we'll make the 4th right now by doing a previous frames.append observation. So this will happen each time, right? So we'll append to our previous frames, our current frame, and then we'll remove the oldest one by doing stacked. Well, first we'll stack it, stack frames equals empty.stack, because the previous frames is going to be a list, right? So we want to change it to a numpy array. And then once we do that, we can say previous frames equals the previous frames negative in frames -1. Yeah, that looks good. So what's actually happening? First, we're checking if our previous frames is empty, we want to fill it up with 3 observations. Then no matter what happens, we always append 1 observation. And then we have our stacked frames is going to be, basically, we're just turning our previous frames, right, which should be 4 observations long now, into a numpy array. And then because we have 4 here, we're going to want to remove 1, so the next time around, we don't just keep building on this, right? We always remove the oldest frame, or we add the newest frame and then remove the oldest frame, add the newest frame, remove the oldest frame. So we always stick with having just 4 frames. And then what we can do is go ahead and return our observation, or sorry, not our observation, our stacked frames, which is like our now our pre-processed data, and the previous frames, just so we can keep track of that too. Cool, so this should ideally work. Let's give this a go too. So let's run that. And we're going to say our pre-frames is going to start out being an empty list, right? And then now that we have an observation, okay, so we have our observation, and we might want to first pre-process it. So we'll say filtered observation equals filter obs, pass our observation in here. So now we have our filtered observation should, yep, looks good. Just double checking, looks good. And now what we can do is we can say we can stack our frames. So essentially what this function should do right now is it should give us 4 of the same frame. The reason being is that, you know, it's the only frame we have so far, so it should kick in this this if statement right here, which should copy the same frame 3 more times. So if we do a get stacked obs, we pass in our filtered observation, and then we give it our previous frames. Now this should be our, I guess we'll call it like stacked observation in the previous frames. This. So now what should happen is if we check stacked obs, we should have a numpy array that has 4 different channels, right, or 4 different frames, which is exactly what we have. So that's good. And ideally, each one of these should equal each other. So if we do everything, or how do we want to do this? So yeah, so the stacked obs 0 should equal stacked obs 1. Oh, we should probably put them all around this. So we're just making sure that all these frames are the same, which should equal 2, which should equal 3. There is no 4. Cool. And you know, via the transitive property, now we know all of these are equal to each other. Cool. So we know that's right. The next thing we might want to check is our previous frames. There should be 3. There should be 3 frames here, right? Yep, 3 frames, because we copied this 3 times, we add another one, so our stacked frames is now 4, but then we remove the most oldest the oldest frame, which leaves us with 3 in our previous frames. Cool. So this looks good, and we should be able to do the exact same thing again if we want, and we should just get the exact same thing, right? Because we're just adding the same frame and getting rid of the oldest frame, which is the same frame. So yeah, that's still 3. And if we check stacked obs, this should still be, yep, 4 channels. We're good to go, it looks like there. Again, I've done more testing in the background, so I can assure you this does work. Yeah, I don't think hopefully it's not too complicated. But that's sort of the pre-processing we want to do on the observation. And that's all we have to do there, which should, you know, pretty cool. Not too bad. And the last pre-processing we're going to want to do is we're going to be wanting to format the reward. Now, why do we want to format the reward? And the reason is that what if sort of like, I guess especially if you're dealing with a lot of Atari games like in the paper where they run benchmarks on lots of Atari games, not just one, you kind of want the reward to be sort of constant and normalized. It just helps out a little bit to keep things steady, I guess, keep everything the same, and then they don't have to do as much fine tuning per individual environment. So in the paper, they use a very simple scheme, which is simply any negative reward becomes -1, any 0 reward stays at 0, and then any positive reward becomes positive 1. So that's exactly what we're going to do. So once we get this reward in here, we're going to say if reward is greater than 0, return 1. Else if the reward is less than 0, return -1. If none of that is true, we just return 0. Awesome. So now if we format reward, -0.5 should get us, yeah, -1, -1, 0, 0.5, yep. And then even a big number like this should still get us 1. Looks good. So we have our formatting functions done. And this will really help us. Now we can actually also start passing observations directly into the DQN. We won't be doing that this episode though. Now what we want to do is work on the experience replay. So what is the experience replay, you might ask? And that is a great question. The experience replay is essentially the way that, so let me get out, sorry, I'm preparing a little algorithm here. Here we go. So what is the experience replay, you might ask? Good question. The experience replay is basically what stores, when we're playing through all these games or all these episodes, it's what stores our data. It stores the transitions that have happened, what actions we've taken in what states, and what rewards we got. And the reason we do this is so that anytime we can go back, grab some of the data from what we were doing, and keep training on it. This is what's called an off-policy training method. Particularly, like deep Q networks are considered an off-policy training method, because as you update your sort of model, what actually happens is you keep training on old data that was generated with a different model, or an older version of the model, right? It didn't have the same weights, because we'll constantly be using data from the past and the present. It's we basically just store it all, and then we randomly take certain basically episodes and we just train on that. The reason we do that is so you get a good breadth of experience as opposed to just the current thing. There's a few reasons. I won't go into all of them in detail right now, but it helps basically bring up sample efficiency and other good things that we want to have. So that's essentially all it is, right? It just stores our previous game data. So what we want to do is we want to make a way to store that. So we will say, make this with class experience replay. And if that doesn't make complete sense, it should make more sense once we actually start to use this class. So I think in the next episode, you'll kind of see how this really directly plays into everything. So the capacity, this will be how many actual transitions can be stored. So we'll just set the self.capacity equal to capacity. And then we'll say self.data is going to be empty at first, right? So this will store our data. This will be our maximum limit. So first we'll have a function called add step, and this will essentially take in some data and just add it to our data array. Pretty simple, or list to be specific. Come back to that. And then the other function we want to have is called sample. And this is very simple, right? We just give it the number of samples we want, and it should return us that many, or in samples, assuming we have that many. So this is quite simple actually, right? If we want to add data, all we have to do is say self.data.append the step data. And then we just want to make sure that we're not going over the capacity. So we say if the length of self.data is greater than the self.capacity, self.data equals self.data up to the capacity. And all this is doing again, right? We add the data. If we're over the capacity, we just remove the oldest episodes until we are within the capacity. That should be all we need to do there. Now, sample is a little bit more complicated just because we need to format everything. The actual logic is still very simple though. So the n, so this is how many samples we want, will be the minimum of n and the length of self.data, right? Because let's say we only have 5 data points, but we're trying to sample 1 million. Well, we're still just going to get 5 back. You could, I guess, if you want to like copy those 5 data points and reuse them. We are not going to be doing that though. It shouldn't make a huge difference either way because this won't happen very commonly, only in the very beginning. And we'll say indices equals the np.random.choice the range of the length of self.data in, we want in, and we will do this without replacements, which essentially means what I just said, right? If we, let's say we sample 10 from 10, it means we might, or if we sample any amount other than 1, we might get the same ones, right? Once we sample something, it doesn't mean we can't sample it again. That's what replaceable means. We're not doing that though. We only want each one time per sort of sample. I honestly don't know what they use in the paper. I think either way, you'll probably be fine though. So all we're doing here is we're getting random indices that we want to pull from our data. So now we can say these actual samples is an np.as array with the self.data at these indices. So we're just turning this all in. We're just pulling those indices out of the array or out of the list and then turning that into an array, or the other way around. But yep. Now what we want to do is here I'm actually going to convert the data to a tensor format, like a torch tensor format, just so we don't have to do that later on. I think it'll be a lot easier. This is kind of just the same thing over again. So I'll write one out and then copy the rest over, right? So we have state data. And remember, so we're going to have every step, we're going to store the state, the action, the reward, the next state, and then we're also going to record terminal data. This isn't always recorded, but this will tell us if the state is terminal or not, if this is the end of the episode. We want that for a good reason that has to do with the training that I will explain later. But the way we're going to format this is just say state data equals torch.tensor. Now we want to stack the samples. Let's see, we want to then convert this to a float. And then I am personally going to be using the GPU for everything I do here. If you're on CPU, you'd probably want this to be well, I think it's CPU by default. But I will be using the GPU, so I do .CUDA. So all we're doing is we're going to the samples, we're grabbing the first sort of row of I guess the first column of everything, which should be our states. And we are then stacking that up and turning it into a tensor, converting that to a float, and then putting that on the GPU. Now we're not actually gathering any of this data yet. I already have it planned out how we'll do it though, so I know this format is going to work for us. It's not like the only way you can do it though. And then we'll basically just do the same for the actions, the rewards, the next state data, and the terminal data. The only things we are changing is the actions will be of type long, or int if you want to do that. And then we're also changing the columns we're grabbing from. But once we do this, we should be able to just return all of this now. So let's see if we get any errors. So let's try making this ER capacity. Oh, yes, I need to give it the capacity. So we'll say maybe it can store maximum of 5. Awesome. So what we want to do now is let's make just a sample data is going to be like, maybe our state is going to be np.zeros to 10, or I guess we're going to do, what is it, like 4 by 110 by 84. And then what are we passing in? So then in act, so maybe that's like we do act 0, we get a reward of 1. The next state is going to be essentially the same thing but 1s. And then our terminal data, 1 or 0. Data type not understood. There should be, the shape should be 1 tuple, not several variables. So this is our sample data. Hopefully we can do an er.add step and then just put in the sample data. Now if we check the er.data, okay, so there's something in there. So the length of it is what? 1, cool. So if we do this 10 times, remember our capacity is 5, so we should see that this stops at 5. Awesome. And then we should be able to sample, er.sample like say we want to sample 5. Oh, there we go. So this is all our data. So if we do, all right, we return 5 things. So if we look at the first one, these are our states. Yep, it's a torch of size 5 by 4 by 110 by 84. That looks all good. The next thing, right, should be our actions, which should just be 5. Rewards should also just be a shape of 5. And then finally we have our states and our terminals. All looks good to go. Awesome. I believe that's all I had on the schedule for this episode. Probably sorry if it's not the most interesting episode, but we definitely got to get through the pre-processing at some point. And what's really nice is you can probably reuse these functions if you use any other 2D environments. Lots of the time it's sort of the same pre-processing. So you don't always have to just keep rewriting this. Like I always just copy it over from my past projects. But thanks for tuning in. So just a quick summary of what we did. We filtered the observation, converted it to grayscale, resized it, converted the scale from 0 to 255 to 0 to 1 so that it works well in the neural network. We then stacked 4 observations on top of each other, made sure we have a function to format our reward, and then made the experience replay, which is essentially a tub we can kind of put all our experiences into that will then be sort of a place we can draw those experiences from and constantly train off of. And it will also, of course, do this nice formatting for us. Definitely check out the next the next video where we will actually start working on the training and the training function, and hopefully in that video we should actually be able to see the fruits of our labor and have a working DQN that can play like Breakout and you know, other Atari games and whatnot. So thank you again for tuning in. Definitely, if you liked the video, hit that like button and please subscribe. It helps out the channel tremendously and I greatly appreciate it. Thanks again and have a great day.